If I just look at the region of x4, let's say, it looks like it's a local sink. But then x3 also has a saddle behavior. Maybe x2 has a local sink property as well. But the question that we're most interested in is not necessarily the local behavior, but the global behavior of the system. In other words, if this system is allowed to run for a very long time, will it settle into one state in particular? So will it specifically go into 1 point or 2 points? So we have to start asking these types of questions. Because this is just depicting the local behavior. We actually want to know what the long time behavior is. So that's the type of questions we'll start to go through. So that's a nice diagram. Okay. So remind me that okay, so to do that, we must talk about the concept of invariant sets. Okay, so definition. We say that a set, so maybe one and a half more lectures on purely theoretical stuff, and starting next week or Wednesday, my hope is that we'll start to do nothing but very interesting examples. And not basic ones, like interesting ones. So this will pay off, my hope. Okay, so we did say a set S, which is a subset of Rn, is an invariant set. Means that for all x, so for all points in this set, and for all time, the flow evaluated at that point is in the set. So that's what we mean by invariant. Common. So what does this mean? So we can say the following. If S is an invariant set, and at some point, let's say x0 is in this set, then the orbit, which I defined for you last time as gamma of x naught, belongs to S. So in other words, if I start in my invariant set, I have to stay in my invariant set. That's another way of it. So my orbit at this point does not leave the set. So what is an example you know right off the top of your head of the simplest invariant set? No. Think about it. Equilibrium. Right. Yeah, okay. Okay, yeah. You want to be as general as possible. But does everybody understand why the equilibrium point is an example of invariant set? Because, as I said, the equilibrium point stays in the system. So an orbit applied to an equilibrium point doesn't change the position of the equilibrium.
Okay. I was thinking when you're going toward, yeah.
Think of it, so the equilibrium doesn't change its position. Exactly. So it's the simplest example of invariant set. If I'm at an equilibrium point, I'm always at that equilibrium. So that's the simplest example of invariant. Okay. But there are more. So, example. So the best example is an equilibrium. And also periodic orbits as well. So we talked about this last time. Where if you are stuck in a periodic orbit, you must return to where you started from. So by definition, that's an invariant set. Okay. So the question is, given a differential equation, how can we find the invariant sets of the dynamics? So there's a trick, actually, to do it. And this trick, for some reason, is not well publicized. So I'm afraid if I tell you, you'll know the secret. And I don't want to give it away, because I use it all the time. But then, okay, it's okay, I should tell you. Save you from reading it. Okay, so how to find invariant? So I'm spending time on this because it's an extremely important idea. So there's a bit of an algorithm, I guess, but it's very straightforward. So given a dynamical system on Rn and some C1 function, so remember this means that it has continuous first partial derivatives, and call this function z, capital Z. And it goes from Rn to Rn, or Rn to R, so it's a scalar function. And let me denote the derivative of Z along solutions of the dynamical system or along the flow, what I really need to say. Somebody's put their phone, I'll chalk this phone. It's okay. Should I move it here for you maybe? So, the question is the following. If I have a function that represents solutions to my dynamical system, how can I describe solutions along the curves of that solution? What type of derivative? Say it again?
Directional.
And specifically, what about the directional derivative? Great, who said it? Great, very good. Same thing. Good. Okay. So in other words, we can define the derivative along solutions as the gradient, which measures how much you're moving along the curve itself. Right? So Z prime then is defined as gradient of Z dot product with f of x, where f of x is the right-hand side of my dynamical system. So remember, we have x prime is equal. So the dot product of this function z with respect to f tells you how solutions are moving along the curve. So in the diagram before, that's how I got the arrows along the curves. The arrows tells you the direction in which solutions are moving. So that's a definition, what we mean by z prime. Okay, so proposition. Consider, once again, my dynamical system, x prime is equal to f of x. Okay. If I can define a function, let's say z, that goes from Rn to R, which satisfies the following. Let's say z prime is equal to alpha times z, where alpha is some function, let's say Rn. So, if you do your work and you come across a system of differential equations, and it has this nice form, one of the equations in your list, where z prime is equal to alpha z, where alpha is some function. So if you can uniquely write it like this, one of the equations, or a multitude of the equations in your dynamical system, then you can say the following. Then, we have that z greater than 0, z equal to 0, or z less than 0 are in fact the invariant sets of the dynamic. That's the trick, how you find invariant sets. Yes?
Gradient that would be like a rescaling pattern?
It's how you measure how the solution is moving along, in what direction and what speed along the curve of the That's what you mean by gradient, right? So
Yeah.
that's the basic. Yes.
So for this statement here,
Yes.
is it could be one of them or all of them or a mixture?
Or a mixture of them, or all of them, or.
Okay.
So let's see an example. So let's say I ask you to solve, let's say x prime is equal to sine y times x, and y prime is equal to x squared plus y squared. So a nonlinear system of equations. What would be the invariant sets of this dynamical system? So which one of these, so this is a coupled system, it's a nonlinear system. Comparing to the definition there, which of these equations matches that definition? The first one. Right? And you can't write the second one as some function times y. You can only do it to the first one. So therefore then, what are the invariant sets of the system? Sure. Somebody said. So what are the invariant sets then? It has to be x is greater than 0, x is less than 0, or x is equal. Right? Just by applying that. So therefore, if you look here, this is the same alpha times x. So therefore, x greater than 0 is an invariant set, or less than 0, or equal to 0. It depends on the case. This is a simple example. I just want to illustrate the definition. Does everybody understand? So it's that simple. So if you can look at your system of equations and you can write any one of them in that form, then you can immediately pull out what the invariant sets are. And this is a very useful trick because it's very difficult often to find out what the invariant sets of the system are, aside from solving for the equivalent. Any questions on this? So I just wanted to illustrate. It's very important. So why am I talking about invariance? Why am I mentioning this? It's the following. So before I say this, let me introduce the concept of what you mean by a monotone function. So a thing that is very also important in dynamics. Okay. So let S be an invariant set. And let Z define from the domain of S to R. So now my function Z, its domain is this invariant. It goes to R. Okay. We say that Z is monotone decreasing or increasing. So I'll put increasing in brackets just to save room. If the following is true, Z prime, which I defined as lambda Z dot F, is less than 0. So if you compute this derivative and it's less than 0, we say that the function is monotone decreasing. If it's greater than 0, it's monotone increasing. So that's how you tell whether a function is what we call monotone decreasing or increasing. You compute the Z prime, you fix it within some invariant set S, and you observe the sign of it. So that's what it means to be monotone decreasing. And why is this significant? It is significant because of the following. Significance of monotone function is the following. So, if there exists a monotone function or monotone function Z from S to R, where S is some invariant set once again, Then, this set S, we can say, contains no equilibrium points, periodic orbits, or homoclinic orbits. In other words, if you have some very complicated, now notice this, I told you what the invariant sets were without actually having to solve or plot or do anything with the system. I looked at it, applied the proposition, and immediately told you what the invariant set was. Okay, so now you can have some very complicated system of equations, and you won't know how to solve it. Maybe it's even hard to find what the equilibrium points are, because you're solving nonlinear equations. But if you can find an invariant set and also a monotone function corresponding to the invariant set, then what that tells you is that in that set, you will not have any equilibrium points or complicated orbits. So it saves you a lot of work. It simplifies the type of solution you will have immensely. Finding monotone functions is another story entirely. Yes?
Okay, so just to clarify.
Yeah.
Okay, so when we have the gradient of, let's say, V,
Yes.
that says at some point what is the fastest rate of change?
In what direction and yes.
So then applied to this, is that saying that, so let's say it would be positive?
Yes.
Does that mean that if every point along the solution or whatever, that it would always be, I guess, going away from something?
Exactly.
So that's why it would never be zero?
Exactly.
So it would be equilibrium, right?
Exactly. That's a fantastic way of thinking. Okay. So, but as I said, as you'll see next week when we do examples of trying to find monotone functions, it's a pretty hard thing to do. So, but if you can do it, you can simplify your life tremendously because the set you're working in now has none of this extra stuff you have to worry about. So you can jump into it. You can not worry about it. So a lot of mathematicians spend a great deal of time looking at dynamical systems, trying to find invariant sets and or monotone functions. Because it allows them to simplify the problem tremendously. But it's not a trivial thing. Because we're not anymore in the land of solving linear equations to get equilibrium points. Try solving this system. It's not that difficult because I wrote it down. But you can imagine something more general. It's pretty hard to find. Okay, so let me now move on from okay, so as I go back to that triangle diagram I drew before, we have two types of behaviors to worry about. One is what behaviors look like in the local vicinity of some equilibrium point. So the x1, x2, x3, x4, but also the global behavior, as I said. So this type of stuff, finding invariant sets, monotone functions, will help us tremendously finding the global behavior, the long-term behavior of the system. But also we should talk about what it means to talk about local behavior in equilibrium. So let me mention some things about it. And my hope is now you'll start to see some interesting. So, behavior near equilibrium. So, let me go back to the land of linear differential equations for a second. So go back to my case where x prime was this matrix A times x. So linear dynamical system. Let me go back there for one. Okay. And of course it's on Rn. And now, once again, let me consider the eigenvalue of A. And remember, these can be complex and not necessarily distinct, right? So the most general case I'm asking you to consider. just look at the eigenvalues of A and also the associated eigenvectors. Okay. So, we can talk about a linear dynamical system entirely in terms of the eigenvectors. And I don't mean solutions, forget about solving it. I want to be more descriptive than that. So what do I mean by it? I mean the following. So, related to these eigenvectors, there are three subspaces of Rn. Namely, we call one a stable subspace, which I will denote by E with the S at the top. And this is simply span of S1 to Sn. I will explain what the S1 to Sn means. The second subspace is the unstable subspace. I've never written so much in my life. Which I will denote as E with a U at the top, for unstable. And this is a span of some vectors, call them U1 to UN. So that's the stable subspace, you have an unstable subspace, and you have one more which we call the centered subspace. And you can imagine, I will call it EC. And this is span of C1 all the way to C. Now what are these? They are the eigenvectors corresponding to the negative eigenvalues, positive eigenvalues, and zero. This is why I was leaving the case of the zero eigenvalues till now, because I wanted to put it in a more general context. So in other words, where S1 to Sn are the eigenvectors corresponding to my negative eigenvalues or more properly with the real part of the eigenvalues. So real part of lambda is less than 0. U1 to Un is the same thing but for the positive eigenvalue. So where the real part of lambda is greater than 0. And then C1 to Cn is where the real part is 0. So, in other words, I can write Rn as the following. E as composed with EU composed with EC. I can describe Rn completely in terms of its stable space, unstable space, and center space. Does everybody know this notation? The cross with the circle around it? It means direct sum from linear algebra. You don't need to know too much about this.
Just a small typo then.
Sorry?
Is there a small typo on the second one?
You tell me, yes, there is. You're trying to test me. Okay.
Are you testing us? Which?
Not as yet, at least. Okay. So the idea is the following. I'll show you an example. You know how to do this. Maybe not written out like this, but you know how to do this. You can describe Rn completely in terms of its stable subspace, unstable subspace, and center subspace. That's remarkable. But apparently I'm the only one that thinks this. I don't know why. So go back to your exam question. You'll see what I mean. So I wrote it down because I forgot what it was. So let's say you had to solve x prime. Or let's say we're not that much interested in solving these things anymore because we cannot do it in the Monotone case. So your first exam question was something like this. 1, 1, 4, 1, x. And now we're not even going to write it in matrix form anymore. I'm going to just, like I did for the first example, I'll write it down in equation form. Because there's no point. I can't write a nonlinear system in matrix form. So let me do it here. So this corresponds to the system. X prime is equal to x plus y, and y prime is equal to 4x plus y. What are the eigenvalues and eigenvectors of this matrix? So say I don't care about solving anymore. I'm just asking you, based on what we've done, what are the eigenvalues and eigenvectors of this matrix? So if you remember, well, maybe you don't remember, but if you did it on your exam, one of the eigenvalues was 3, the other one was -1. And the eigenvector corresponding to 3 was 1, 2. The eigenvector corresponding to -1 was -1, 2. I believe that. Okay, so now let's look at our definition. What is the dimension of the space of my system? So it's R2, right? Okay, that's the first thing. Good. How many positive eigenvalues do I have? So how many eigenvectors do I have corresponding to the positive eigenvalue? How many negative eigenvalues do I have? And how many eigenvectors do I have corresponding to the negative eigenvalue? How many zero eigenvalues do I have? So what is the dimension of my stable subspace? Why is it 1? Remember, what does it mean to have a stable subspace? It only contains the eigenvectors with negative eigenvectors. What is the dimension of my unstable subspace? And what is the dimension of my center subspace? Very good. It's that simple. You know how to do it. It's just the terminology is confusing. So we can write that R2 is decomposed into ES and E. Where the eigenvectors, it's a vector space, so they'll contain vectors. But the vectors that these spaces contain are the eigenvectors. So for ES, this is simply the -1, 2. And this is simply 1, 2. It's that simple. So let's do another one. I'll do the second example. And you see, now we can tell you a lot about the solutions of the system qualitatively, because we know what it means now to have a stable section of my space grid and an unstable. So I know now what the orbits are going to do in the vicinity of these equations. And I know where they're going to do them further, because I know what these are. I can draw these up. Okay. So the second exam question. Was slightly more complicated, but it was -3 √2 minus 2x. And you found that the eigenvalues of this, or at least I hope you found, was -4 and -1. And the eigenvector corresponding to -4 was -√2, 1. And for -1 was 1 over √2. So, what is the dimension of the system? R2. Now, how many zero eigenvalues do I have? How many negative eigenvalues? And how many positive eigenvalues? So I only have a stable substrate. So R2 completely, where ES now, if you want to write it up, is the span of these. So minus 2, 1, 1, 2. That's it. So we can, as you can start to see, we can tell you a lot about solutions to an equation without actually ever having to solve it. Yes?
Okay, so you're saying that R2 is equals to stable substrate?
In this case.
So what happens, okay, so let's say you're given R2 is equals to purely a stable substrate?
Yes.
And then you also say R2 is equals to a purely unstable substrate. So aren't you describing the same vector space, but if you're saying it's different?
How can it be in this case, though, that you have an unstable subspace?
No, I'm saying another example where R2, let's say, is...
Oh, so that's right. So we fix Rn to be context dependent on the system we do.
Okay.
So it's more abstract, but at the same time, we just assume everything is in Rn. But yeah, don't get confused. This is a different R2 than the R2 we had done before. Now, if you can find a homomorphism that relates this question to the other one, then they're the same, as you know now. But in general, they are different. So in this case, the entire phase plane is a stable substrate. So all orbits in this system approach the equilibrium. Every single one. In this situation, you'll have some of the orbits that will approach this direction, but they'll be repellent this way. So you have a way of qualitatively describing this. Is that clear now with an example? 2 examples? More or less? Okay. So I will. Okay. I hope I erased the right word. Yeah. In my morning lecture in calculus, I wrote one board. It took me about 11 minutes to write, and I erased it, not knowing what I was doing. I upset a lot of students because I disrupted their note taking. It's not good. Okay. All right. So that's linear system. So now that we understand what we mean actually by describing the behavior of solutions of linear systems, let's go back to the general nomenclature. Because as I said, this works great when you have the coefficients of numbers. I can immediately write down what the eigenvalues and eigenvectors are. But in the nonlinear case, I cannot do this. So what do I do? So how can I describe now solutions for full nonlinear? And the idea is to, it's called linearization. As you may have imagined. And in particular, the fundamental theorem here is called the Hartman-Grobman, which I will not prove. I will not even try to prove. Yes?
Random question. Okay, so...
No more random.
No, random. Like, okay, so you know how when you have a linear system,
yes.
Dynamical system, then you have eigenvalues, eigenvectors?
Yes.
For that system?
Yes.
So let's say we're given a nonlinear system.
Yes.
Is there an analogous thing where you have eigen functions or eigen something?
Yes.
Yeah.
It's the Hartman-Grobman theorem.
Oh, is it?
It's related to it. But yeah, you're right. In general, Eigen functions come from dealing with infinite dimensional vector spaces. They will not show up with Rn. They will show up with R infinity.
There's this thing called eigen functions.
Yes. Eigenfunctions occur in the case where you are trying to find solutions to partial differential equations. So the idea is you can actually, if you want to solve a PDE in the most general way, you can decompose it into an infinite set of ordinary differential equations. And then each solution to that is an eigenfunction. So you'll learn this next year when you do what is called Sturm-Liouville. But it's analogous to this. You have an eigenvalue problem, and instead of solving for eigenvectors, you're solving for eigenfunctions. So I can show you that. to our nonlinear system. So consider, once again, my dynamical system, x prime is equal to the most general. And once again, it's on R. In fact, you can impress your friends when you take PDs, because you can say, I'm working in infinite dimensional linear algebra. They'll be very impressed.
I won't express.
Yeah, they're not impressed when I say that. I don't have any. It's okay. My cat is my friend. He's a very nice person. Okay, is a plus C1. So remember, I'm assuming it's C1 because I want to assume I can do existence and uniqueness. But it's not important. Anyways, consider x prime is equal to. Okay? If A is an equilibrium point of this system, so what does it mean once again if A is an equilibrium point of this system? How do I write that? Very good. So if that condition is true, then what can we see? Then we can say that, oh, the linear approximation of F, which is the right-hand side of my dynamical system, at this equilibrium point A, is given by what? Multivariable people, what do I do? Taylor.
Just use the first two. First two.
Two would be sufficient. You can do three if you want. Two is sufficient. So f of x, I can approximate by, as Don said, the derivative matrix, which I will call dfa, evaluated at some point x. What in the world is this df of a? It's the Jacobian matrix, where df of a is given by df of I dx. Or if you want to write it on matrix form, which is more useful, I guess, recall that it just looks like this. So df of 1, dx1, all the way to df1, dxn, dfn, dx1, all the way to df1. So your right-hand side is a vector field. So you have f1, f2, f3, just like it did before. And this is how you take a look at Jacobian. And we evaluate each one of these derivatives at A. So you get a number. So, for a nonlinear system, yes?
That matrix is a part of the equation?
No. I just mean it's this. So df of A, which I call the Jacobian, is this. You've seen this before, right? Jacobian matrix, I hope. Otherwise, I'd be very foolish right now. Okay. So, in other words, for a nonlinear system, if I know what the equilibrium points are, I can describe something about that system in the neighborhood of the equilibrium point by computing the Jacobian matrix. And we know how to do this because we know what f is. It's given to us. So it's very easy. So what can we say? So what is the hope of doing this? Why do I want to do this? And my hope is the following. That the solutions, so let me denote this just for, well, okay, one second. Before I write my hope down, let me say something. So then I can transform my dynamical system from x5 to fx through this linear approximation. Namely that, let's say, U prime is equal to df at A of A. So by doing this approximation, now I can state my goal. And let me call this for brevity equation star, second and third. The hope is that the solutions of my linearized system, star, will approximate the solutions of the nonlinear differential equation. In a neighborhood of the equilibrium point A. So that's how I do nonlinear dynamics. I keep taking linear approximations in neighborhoods of my equilibrium.
Is this equivalent to when you did manifolds, when you said you can approximate the manifold with an Rn in that local area?
That's exactly what I'm doing here too. Because what technically have I done by doing this linear approximation? By introducing a matrix, I've introduced a vector space. So my curved nonlinear system is some manifold, and now in my tangent space, I'm doing this derivative approximation. So that's why I talked about it. So that is the machinery I rely on. But the hope is this. So if I can solve the linearized system, it will approximate solutions to the nonlinear system. And in fact, that is the statement of the Hartman-Rubin group. So I will just write down one more definition, then we will continue on Monday. So definition. So, given, once again, x prime is equal to f of x, and in equilibrium point, x is equal to a, we say that this equilibrium point is what we call hyperbolic if all eigenvalues of my Jacobian matrix, so df of A, have non-zero real parts. So, if you compute the eigenvalues of this Jacobian matrix at that point, and they're all non-zero real part, we say those equilibrium points are hyperbolic. And I will continue from here on Monday. I just find it remarkable that people realize that you can determine stability properties just by looking at signs of eigenvalues. The fact that Poincaré, who was the person that basically came up with this stuff, Hartman and Rubin formalized it many years later. But the fact that he's given a nonlinear system and says, yeah, look at the eigenvalues of the Jacobian. I think that's genius, but